In example 5 on page 32, we are going to look at two more examples of cyclic groups. So let G1 be the group of rotational symmetries of the regular pentagon and G2 be the group of rotational symmetries of the regular hexagon. And to help us find out what is really in these groups, I've drawn a regular pentagon over here and a regular hexagon, and I know they don't look very regular, but just humor me for a second. So here we have our pentagon, and so how can you rotate that pentagon to put it back into its original position, or so that you can't tell that you moved it? Well, you can rotate by 72 degrees. So this angle right here, that is 72 degrees. And so if we rotate by 72 degrees, then this vertex moves to the vertex on top. And if you didn't look while somebody moved it, you see that the pentagon looks just the way it was at the beginning, even though you did rotate it. So let's call that rotation alpha. So alpha is the rotation by 72 degrees counterclockwise. And similarly for the hexagon, if we have a hexagon, we can rotate it by 60 degrees and get our same hexagon back. And so let beta be a rotation by 60 degrees. If we just name those two rotations, then we can describe all other rotations just as powers of those rotations. So what other rotations are in the group of symmetries G1, the rotations of the regular pentagon? Well, 72 and then 144 degrees, that would be alpha squared, and then another, put on top of that, another 72 degree rotation, that gives you alpha cubed, and then you do it one more time and that gives you alpha to the fourth. If you do it one more time, you get alpha to the fifth, but that's your identity back. And the same way with our rotations of the regular hexagon, we have a 60 degree rotation, 120, 180, 240, 300, and then 360 degrees gives you your identity back. So those are the two groups that we are going to investigate in this example. And the first thing they are asking us to do is to make a circle diagram similar to what we already did before to illustrate what is happening in our two groups. So instead of drawing my pentagon, I'm just going to draw a circle that has 5 points on it. So let's say I have one here, one here, one here, one here, and one here. And they are not particularly regular, but again, just humor me. So we are starting somewhere, let's say here, that's alpha. And then we're going and we get alpha squared. And then we get alpha cubed by just taking powers. Then we get alpha to the fourth, and then we get alpha to the fifth, which is also our identity element. And let's use this little epsilon as our identity element in this particular case. Then if you take another power, alpha to the 6, you're back where you started. It's just equal to alpha. And if you did it again, you'd get alpha to the 7th. And then you'd get alpha to the 8th. You'd get alpha to the 9th, and so on. So we can just go round and round and round in our little circle diagram to illustrate what is going on in the group G1. We can do the same thing with our group G2. So now we have our hexagon. So let's say here's my hexagon. Somewhere I'm going to put my circle around it. And so I have beta somewhere. Then I have beta squared, beta cubed, beta to the fourth, beta to the fifth, beta to the sixth, which is my identity rotation, the don't move anything rotation. And then I'd keep going. Beta to the 7th is the same as beta. Beta to the 8th is the same as beta squared, and so on. Beta to the 9th, beta to the 10th, beta to the 11th, and round we go. So we have our typical cyclic representation of our groups. Now, the question we want to investigate is, for both of those groups, which powers of alpha are actually generators for both of those groups. So in part B, we're going to look at group G1, and I want my diagram right here. So let's see, it's going to help us. So if I take alpha and take it to higher and higher powers, well, we can see in our circle diagram over here that if we're just starting with alpha and then go alpha squared, alpha cubed, alpha to the 4th, alpha to the 5th, which is the identity, I get my entire group. So let's write that down. So I have my identity, I have alpha, alpha squared, alpha cubed, alpha to the 4th, and that's my entire group. What about if I started with alpha squared and took powers of alpha squared? So what if I went with alpha squared and I take powers of alpha squared? So alpha squared squared, that is alpha to the 4th. Okay, and then if I multiply by another alpha squared, I get alpha to the 6th, which is alpha. And if I do another power of alpha squared, I come up with alpha to the 8th, which is actually alpha cubed. And another one would give me alpha to the 10th, which is the identity. So again, I am generating my entire group. In a different order, I first have alpha squared, then alpha to the 4th, then alpha to the 6th, which is the same as alpha, and then I finally pick up alpha cubed. So I get everything, every group element. And you can convince yourself that the same thing is happening with alpha cubed. So if we take it to the 0th power, we get as the identity, then we get alpha cubed. Then if we take alpha cubed times alpha cubed, it's alpha to the 6th, which is just alpha itself. And then the next one is alpha to the 4th, and the next one that I'd pick up is alpha squared. So you can do this a little bit more slowly and convince yourself that you get everything. But again, it's our entire group. And even with alpha to the 4th. So you would start with alpha to the 4th, well, the identity, then alpha to the 4th. And then if you take alpha to the 4th times alpha to the 4th, you have alpha to the 8th, which is the same thing as alpha cubed. And you can go around your circle diagram and see that that's the case. And then the next one would be alpha squared, and the next one would be alpha. So it looks like every non-zero power generates all of G1. So that is one thing that we can say here. All non-zero powers generate our group G1 for the rotations of the pentagon. Let's see if that's also going to happen with our group beta for the hexagon. So I may have to do some, let's zoom a little bit so that we can still see our circle diagram. So what do we get when we take beta to higher and higher powers? Well, the 0th power, that's just the identity. And then we have beta squared, we have beta cubed, we have beta to the 4th, beta to the 5th, and then beta to the 6th is the identity again. So we have everything just going around our circle once. What about with beta squared? Let's see what happens here. I'm going to change colors, and we are starting with beta squared. So if I take beta squared and square it, I'm basically skipping the next point. I'm going straight to beta to the 4th. So I had, well, the identity, I have beta squared. The next one I get is beta to the 4th. And then what do I pick up? I skip beta to the 5th, and I get beta to the 6th, which is just the identity again. And then the next one would be beta to the 8th, which is beta squared. So I'm not getting everything. I'm just getting the identity beta squared and beta to the fourth. What about for beta cubed? What if I start with beta cubed? So I'm starting over here, and so now I'm going from beta cubed, I'm squaring it, so beta cubed times beta cubed. That gets me directly to beta to the 6, which is the identity. And then, so I'm basically skipping 2 powers of beta and going directly to beta to the 6, and then I would skip 2 again and pick up beta cubed. So I'd be just going back and forth between the identity and beta cubed. So this is just the identity and beta cubed. Getting a little bit colorful here. What about with beta to the fourth? You can convince yourself that you start with the identity and then we have beta to the fourth. And then are we picking up something new? So it's getting a little busy, but so we're starting with beta to the fourth, and then beta to the fourth squared is beta to the 8th, which is the same as beta squared. Oh, I circled the wrong one. Let me fix that. That's why I was irritated here for a second. I actually wrote that down wrong. Can't read my own handwriting. I wanted to start with beta to the fourth. Yeah, right here. Beta to the fourth. And so from beta to the fourth, I'm going to beta to the 8th. And then from beta to the 8th, I'm going to beta to the 12th, which is the same thing as beta to the 6th. My picture gets really, really busy, but I'm just picking up the elements, the identity, beta to the fourth, and beta squared. And if you do the same thing with beta to the 5th, you have the identity, then you're coming up with beta to the 5th. The next one would be beta to the 10th, which is the same thing as beta to the 4th. If you're taking that times beta to the 5th, you have beta to the 9th, which is beta cubed. And then the next one you'd pick up is beta squared, and then the next one you'd pick up is beta. You can convince yourself by going around the circle diagram. It's just getting a little messy right now. But looking at this, what do we observe? We observe that we only have 2 generators in this case. Beta is a generator and beta to the 5th is a generator. So only beta and beta to the 5th are generators of our group G2.